So till now we worked on the single degree of freedom systems. Now let's take a look at the multi-degree of freedom system. So equation of motion for multi-degree of freedom systems. So let's write the energy functional, or the first variation of the energy functional. The total energy functional is as follows. We can also call this as the virtual work expression. So I'm just writing it for the most general case. So volume, the variation in the displacement multiplied by the body forces integrated over the volume. Plus I can have a surface loading. So the displacements multiplied by the surface load integrated over the surface, and I can have point loads. So I is equal to 1 to n displacements at discrete locations and the applied point load. So this part we can just say that work done by external forces. So they should be equal to integrated over the volume. Now I have the strains multiplied by the stresses, that's the internal strain energy, plus the displacements multiplied by the, there's no dot here, multiplied by the inertia forces, which is equal to rho times u double dot, and plus the displacements multiplied by the viscous forces integrated over the volume. So this part is the one that we discussed previously. That's the internal strain energy. Okay. So this part is inertial work done by the inertial forces. And this one is the work done by the viscous forces. So for the most general case, we can write the energy equation as follows. The first variation of the energy equation. So in this equation, let's write it this way. Rho represents the material density. Kd represents the material damping. And here Fb is the body forces, Fs surface forces, and Pi is the concentrated loads. Okay. Now we can write this energy equation for the whole system or for a single element, right? And let's say that I have a single element, and in that element I'm using the finite element interpolation, and say that displacements are interpolated by some shape functions multiplied by the nodal displacements, and I can use the same shape functions to interpolate the nodal velocities as well as the nodal accelerations. Okay, so I will call this energy equation as 1, and now these interpolation functions as equation star. So if I inserting star into equation 1 leads to, so I'm just taking in parentheses, I have the first variation of the displacements. I have the volume integral B transpose multiplied by the stress times dV plus the volume integral rho times n transpose multiplied by n times dV multiplied by the u double dot plus again integrated over the volume material damping multiplied by n transpose n times u dot dV, and we have the forces. So I will not write all the forces but just the body force, volume n transpose F body integrated over the volume must be equal to 0. Okay. So this part, remember that we worked on it. This is for the static case, by using this part of the equation, we calculated the stiffness matrix of an element. And this part is what we call the consistent load vector. So these two parts, we worked on it. Now we have this equation and that equation. Okay, so let me rewrite that. Let's call this one equation star and star. So I'll say that we can further write equation in the following format. So here I have mass matrix multiplied by the accelerations plus damping matrix multiplied by the nodal velocities plus the stiffness matrix multiplied by the nodal displacement should be equal to externally applied loading. Now in that case, the mass matrix can be calculated by rho n transpose times n and integrated over the volume. And if you calculate the mass matrix in this following form, this mass matrix is called consistent mass matrix. We call it consistent because we are using the same shape function that we used to interpolate the displacement, velocities and the accelerations. Okay, and with these functions we use the energy equation, and the mass matrix calculated in this way should satisfy this energy equation. That's why we call it the consistent mass matrix. For the damping matrix, has the same format. We have the material damping, we have n transpose times n integrated over the volume, and this is called the consistent damping matrix. So the equations, the way we derive the equations tell us that we can calculate the damping matrix as follows. But really, this doesn't, when you do it this way, it doesn't work for the solids. Okay, this could be good, this approach could be good for Newtonian fluids, but in the solid mechanics, this type of damping is not very effective. We have other types of damping. We call them internal and structural damping, which we will talk about. So that's why in the solid mechanics, we don't use damping formulation in the following format. So let's put that as a note. This is for Newtonian fluids. Where viscous damping is effective. Okay, in solid mechanics, we don't have viscous damping, but instead of the viscous damping, we have the internal and the structural damping. So that's why we don't use the damping matrix in the following form. Now what we are going to do is, up to now, we know the construction of the K matrix for different actions. That's what we have learned. Now we will be looking how to construct the mass matrix. What are the problems? What are things that we should be very careful? And also we will talk about the damping, construction of the damping matrix. After that, we will again discuss the numerical integration one more time and then finalize this topic. We will first discuss the mass matrices. Remember that we find out that the consistent mass matrix should have the following form: N transpose N and integrated over the volume. And we said that that's the consistent mass matrix. Now let's start with again our simplest element. So let's calculate the consistent mass matrix of a truss element. So this is our truss element. That's node I, node J. That's the length of the member. And we have U1, U2, and we also have V1 and V2 here. Okay. Now I'm just defining a coordinate system as follows. Let's call it S. And the shape functions for the truss element is defined as follows: L minus S over L and S over L. And our degrees of freedom, the active degrees of freedoms for this element is U1 and U2. So if I want to calculate the consistent mass matrix of this element, I have to do the following. Integrate over the volume. I have rho N transpose multiplied by N integrated over the volume will give me rho times A integral from 0 to L N transpose N times ds. And when you evaluate that integral, at the end of the day, we got rho times A times L divided by 6. I got 2, 1, 1, 2. So these are the stiffness coefficients, mass coefficients corresponding to the translations in the 1 and 2 directions. That's fine, but what about V1 and V2. How can we generate the consistent mass matrix for these two degrees of freedom? Because yes, we may not have any stiffness in these directions for a truss element, but this doesn't mean that we don't have any translational mass. Okay, so we say that, note that unlike stiffness, translational mass never vanish. So we must define translational mass in V1 and V2 directions also. Okay, so in order to obtain consistent mass matrix corresponding to V1 and V2, we can use the same interpolation function that are for U1 and okay. So we are doing the same thing. We are saying that V is equal to n times Vi, and when we evaluate the mass matrix in the following form, we'll have M consistent is equal to rho times A L over 6 2 0 1 0 2 0 1 2 0 and 2. That will be the consistent mass matrix for a truss element, and here the displacement vector is defined as U1, V1, U2 and V2. Here we have stiffness for U1 and U2 directions, but zero stiffness for V1 and V2, but we should have all masses for these two translational degrees of freedom. Now we can generate a consistent matrix in the following way, but when you look at this matrix, you see that it's almost a full matrix, okay? And in the integration algorithms that we calculated, if we have a diagonal form of the mass matrix, then we can perform numerical integration in a more computationally efficient way. Okay, so that's why the other approach while calculating the mass matrix is the lumped mass matrix. So let's take a look at it. Lumped mass matrix of a truss element. So I will just draw the same truss element. We have U1, U2, V1 and V2. So what we do in the lumped mass matrix is we divide the structure into half, and the half of the mass is lumped to the start node. The other half is lumped to the end node. Okay, and the magnitude of that is 1 over 2 rho times A L. Okay, so we are just lumping the masses to the nodes for translations. We call it direct lumping, and in that case my lumped mass matrix will have the following form. Rho times A times L divided by 2, and I have the same translational mass for each degrees of freedom, and that's the lumped mass matrix for a truss element. So it's very easy to calculate, and at the end of the day you'll get a diagonal matrix. So when you want to invert it, you just invert the diagonals. So that's why in the integration algorithms it's usually preferred to use lumped mass matrices. Now we discussed two approaches to calculate the mass matrix, but the matrix that we obtain at the end of the day must obey the following properties. So let's discuss that. Mass matrix properties. So there are two symmetric conditions. You have a symmetrical matrix and the physical symmetry. So what we meant by physical symmetry is, so if the element symmetries must be reflected in the mass matrix. So the other property is the conservation. So the first thing that you should converse is the mass. The total mass of the element must be conversed, must be preserved. Okay. Then the other conservation law is the linear momentum. Is also something that we have to be conserve, and also sometimes we want to have the angular momentum to be conserved. So this is optional, okay? And sometimes in some problems you don't want to conserve the angular momentum because it may cause other problems in your solution. But the requirements is, first of all, the total mass must be preserved, and you have to be able to preserve the linear momentum. The other condition is the positivity. For any non-zero velocity field defined by nodal values so that is u dot element is not equal to 0, then your mass matrix should satisfy the following conditions. Transpose multiplied by the mass matrix multiplied by the velocity itself should be larger than or equal to 0. So if you just reevaluate that equation, you'll see that that's the kinetic energy. So basically what we are saying is if you have velocity, your kinetic energy cannot be smaller than 0. So that's another thing that should be checked. Okay, how do we check it for a multi-degree of freedom system, for a matrix? We will be looking at the eigenvalues. You shouldn't have any negative eigenvalues for the mass matrix. Okay. So having discussed that, now let's take a look at the consistent mass matrix of a beam element. So this is our beam element. I have V1, V2, and I have theta 1, theta 2 as my degrees of freedoms. That's the length of the member, okay? So by using Hermitian shape functions, and U as V1, theta 1, V2, and theta 2, we obtain the consistent matrix as rho times A times minus 1 to 1 L over 2 N transpose N dx psi. Now the degree of the quadrature rule, if you are doing a numerical integration, is important here. So in order to obtain the exact solution, you need 4-point quadrature for this. And when you evaluate that with the 4-point quadrature, you obtain rho times A times L. Of course, you can always do it symbolically, but if you are doing it numerically, you have to use 4-point quadrature. Numbers are as follows: 156, 22 L, 54, minus 13 L, 4 L squared, 13 L, minus 3 L squared, 156 minus 22L and 4L squared, and that will be the symmetrical matrix. And this matrix satisfies or conserves both linear and angular momentum. Now if you use quadrature point smaller than 4, then the mass matrix that you will get will have singularities in it. It's not then acceptable. So 4 point is the minimum requirement for this type of mass matrix. Now that's the way we construct a consistent mass matrix. But as you see again, this matrix is a full matrix, and sometimes instead of full matrix we prefer to use a lumped mass matrix for computational purposes. So let's take a look at how we can obtain the lump mass matrix. Lump mass matrix of the Bernoulli Euler beam. So the degrees of freedom, we have V1, theta 1, V2, and theta 2 again. That's L. So the translational degrees of freedom is very straightforward. Again, we divided from the middle, lump the half of the mass to the start node, lump the other mass to the end node, so that there's no problem in the translational mass. So we can say that translational masses are okay. So what about the rotational mass? What should we do? So first, before going into that, let's write the lumped mass matrix as rho times A times L. I have 1 over 2 here. For the rotational mass, we can use the form of the mass moment of inertia of a bar. So it will have alpha times L squared. We will determine what alpha is. 1 over 2 is the translational mass. Again, I have alpha times L squared. Now the question is, what is alpha? Okay, so that's an argument going over for the several decades. So the choice of alpha has been argued in which alpha approximates a behavior in a better way. But there's no consensus, okay? So we can just say that alpha is larger than 0, and it's typically between 0 and 1 over 50, okay? But one approach is to ignore this rotational degrees, don't use it at all. So you have an ignores rotational mass. But you have a singular matrix, so your solver should be able to handle that. Okay, that's one approach. And the other alternative is use it as minus 1 over 24. So with this approach, conserves angular momentum. but violates the positivity condition. Okay, so usually we use the lumped mass matrix, but for the energy equivalent, that should be the matrix to be used. It's the consistent mass matrix. Now evaluating it for the two-dimensional finite elements are exactly the same approach. You have the shape functions and you evaluate the consistent mass matrix. What to do with the rotational masses is always a problem, especially in the plate bending elements. What should be the mass matrix for these rotational degrees of freedom is an issue. The lumped mass matrix, again, if you have a two-dimensional element, you just calculate the corresponding volume for each node and use it as a lumped mass matrix.